Today we're going to be graphing rational functions. Here are some of the questions we're going to be answering. What is an asymptote? What is removable discontinuity? How do you determine the asymptote? All these are going to come into play when we graph these rational functions. Alright, so remember from our last lesson, a rational function is basically a fraction. Okay, you're going to have a polynomial over a polynomial. Last class you looked at graphing something that was what we call in standard form. And notice how this is different. Alright, what we're going to be talking about today is when it's not in standard form, when we have a single fraction. So, the following guidelines are things that you need to memorize. So take a moment, read through these on your paper, 1 through 6, and then we're going to apply these guidelines. Let's look at our first example. We want to graph this polynomial function. So we're going to have different cases that we need to look at. Alright, so we're going to ask, what if the polynomials can be simplified? So let's do that. Let's factor the numerator. So that's a difference of squares, so we're going to get x plus 3, x minus 3 over, alright, what multiplies to give you 3 but has a difference of negative 2. So negative 3 and positive 1. So x minus 3, x plus 1. Alright, notice that this polynomial function has a common factor of x minus 3. So x minus 3 over x minus 3 is just 1, so that divides out, leaving us with x plus 3 over x plus 1. We're going to use that to graph our polynomial function. Now, alright, so we got to start answering these following questions. What's a hole? What's a hole in a graph look like? So in our case, a hole in a graph, let's go back to our guidelines. Alright, number 1, a hole in a graph is a removable discontinuity. It happens when we have a common factor. So in our case, that x minus 3 is our common factor. So then we know that we're going to have a hole in our graph. So let's go back. Alright, that common factor. How do we find where that hole is? Alright, well, it's the 0, the x value is the 0 of that common factor. So it's going to be that 3, because x minus 3 equals 0, x equals 3. So we have x is 3. Now we got to find the corresponding y value. Alright, to find the corresponding y value, we're going to plug 3. I'm finding my hole here. We're going to plug 3 into that simplified equation. So my y is equal to 3 plus 3 over 3 plus 1. So 6 over 4, or 3/2. So my graph has a hole at 3/3. So let's graph that first. Let's graph everything we find. Let's graph it as soon as we find it. Alright, so let's graph. So we're going to have 3, 1.5. So there's literally a hole. So draw an open circle to represent that hole. Alright, now we need to find, let's go going down our list here, we're going to look at our vertical asymptotes. Vertical asymptotes. Okay, so let's look at the definition. A vertical asymptote is a removable discontinuity. So it occurs when the denominator equals 0. So our vertical asymptotes are what makes the denominator 0. Once you've moved the common factor, you can't be a hole and a vertical asymptote. You're either one or the other. Common factors are whole, zeros of the denominator are vertical asymptote, which is a non-removable discontinuity. All right, so let's see here. So once we simplified here, right, what makes our denominator 0? So to find our vertical asymptote, we're going to set our denominator equal to 0. So x equals -1. So we have a vertical asymptote at x equals -1. We also know that's going to affect our domain, so that means our range, x cannot equal -1. It also cannot equal your whole value, so x cannot equal 3. So we have two restrictions on our domain. All right, let's graph in that vertical asymptote. So x equals -1. Let's graph that in. Let's change the color so we can see a little bit better when we're graphing these things. All right, so the 0 of the denominator is a vertical asymptote. All right, let's go back now and let's find a horizontal asymptote. All right, lots of ways of doing this. So we got to look at all these different situations. So the horizontal asymptote, all right, is going to be that our graph, so a value that the function approaches is x increases without bound. So we have three different situations we have to. It comes with the degree of the numerator compared to the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is y equals 0. If the degrees are equal to the numerator and denominator, then we make a y equals a fraction, the ratio of the lead coefficient of the numerator over the lead coefficient of the denominator. And finally, if the degree of the numerator is bigger than the degree of the denominator, if it's top-heavy, there's not going to be a horizontal asymptote. I'm going to show you an easy way of doing this, so you don't have to remember these. We're going to one way will get us all three situations. So let's look at horizontal asymptote. Okay, let's look at our simplified degree. We're simplified here. We can look at that. So here, the degree of my numerator. Give myself some room here to work on my horizontal asymptote. Horizontal asymptote. Okay, the degree of my numerator is 1 because my highest exponent is 1. The degree of my denominator is 1. So since the degree of the numerator equals the degree of the denominator, we're going to think about this as 1x over 1x. Simplify that, so that means that my horizontal asymptote is y equals 1. We have a horizontal asymptote. So let's dot that in. Always dot in your asymptote. It helps you when you go to graph. Okay, so now we found, working our way through our list, because we're trying to get points to graph this thing. What happened to my hole? Let's see, let's put that hole back in. 1, 2, 3, 1.5. So we got a hole here. I think when I undid, I got rid of my hole. Okay. All right, x-intercept. Let's go back to my x-intercept. Let's find my x-intercept. X-intercept is the 0 of the numerator. The zeros of the numerator. All right, let's go back. The 0 of my numerator. So what makes my simplified form here again? What makes my numerator 0? I'm finding my x-intercept. So we're going to set x plus 3 equal to 0. So x equals -3. So that means my x-intercept is -3, 0. All right, let's find my y-intercept. My y-intercept is the value of f of 0. So all that means is we're going to substitute 0 in for x. 0 in for x. So let's go with that. So we're going to put 0 in for x. So I'm finding my y-intercept now. Okay, so we simplified version again. We're going to plug, so y is equal to, plug 0 in for x. So that means y equals 3. So 0, 3 is my y-intercept. All right, let's graph what we've got, okay, and figure out what we need to do. We might have to plug and chug to get some more points. All right, so let's graph -3, 0. -3, 0. All right, I can get another point off of that. Remember, this is where I'm counting from. This becomes my new origin. I can cheat and get another point off of that. So from that point, I went left 2, down 1. So now I'm going to do the opposite, because I know that in our most rational functions they're odd functions. That means they're symmetric, 180-degree symmetry to some point. So I mean, I can get another point. So I went right 2 down 1. I'm sorry, left 2 down 1. I'm going to go right 2 up 1. So there's another point on my graph. All right, let's graph the y-intercept. So 0, 3. 1, 2, 3. Now all these points that I find, I'm counting from the origin. Anything I move, I'm counting from that red point, okay, my rotation point. All right, so here I went right 1 up 2, so I'm going to go left 1 down 2 to get another point. I'm trying to get 3 on each side, all right? That helps me get a good picture. 2 if you can't get any more, but 3 makes it better. All right, that hole, I can use that hole. Now, it's not going to be a hole on that rotation side. So I've got, I'm counting from my red dot again, 1, 2, 3, 4, up a half. So left, 1, 2, 3, 4, down a half. It's not going to be a hole on that other piece. All right, that's enough to get me a good picture. So I respect my asymptotes. And my other half, I respect my asymptote. All right, hole, we're skipping over that, is actually literally a hole in the graph. Like somebody took a hole punch and made a hole in our graph. All right, so there's our first picture. All right, let's make sure we filled out all that information. No, we got to do the range. Let's talk about the range. So the range here is all reals, but y cannot equal to the asymptote value, 1, and also the hole value, 3/2. So don't forget about the holes in your domain and range. All right, let's look at another example. All right, what if the polynomials do not simplify? All right, we don't always want to start out by factoring these things, and that helps us to see if we can simplify or not. So let's factor the numerator. So 2 times x plus 3 over x minus 4. This does not have a common factor, so that means there's no hole. Hole is none. All right, vertical asymptote. It's the 0 of the denominator. So what makes my denominator 0? So set x minus 4 equal to 0, so x equals 4. X equals 4. Okay? All right, horizontal asymptote. All right, here again, we're looking at the degrees. I'm going to go back because I want that coefficient. I'm going to look at my original. So the degree of my numerator is 1. The degree of my denominator is 1. Put the degree over itself, equal degrees. So we're going to have 2x over x, which simplifies to 2. So that means that my horizontal asymptote is y equals 2. All right, so let's graph this so what we've got so far. So x equals 4, y equals 2. I don't have any holes. All right, let's find we need some points on this thing. So let's get that x-intercept. That's going to get us a point. So x-intercept, the 0 of the numerator. So x plus 3 equals 0, so x equals negative 3. So I'm going to have negative 3, 0 is an x-intercept. All right, y-intercept, we're going to plug 0 in for all the x's. So y is equal to 2 times 0 plus 6 over 0 minus 4. So 6 over negative 4, so negative 3/2. So 0, negative 3/2 is another point. All right, let's graph what we've got and try to, like I said, we'll rotate those points to get some more. Our goal is to get 3 on each piece. So let's see where where we are. So I know my graph is going to be here and here, or here and here. Okay, let's see. So let's go negative 3, 0. Start counting from the origin because it's a point. 1, 2, 3. All right, I can rotate that. And remember, I'm counting from here where my asymptotes intersect. So let's count how I moved there. So I went 1, 2, 3, 4, 5, 6, 7, and down 2. 1, 2, 3, 4, 5, 6, 7, and up 2. All right, let's do 0, negative 3/2. So from the origin now, 1.5. All right, let's count and get another point. So I'm going 1, 2, 3, 4. 1, 2, 3.5. 1, 2, 3, 4. 1, 2, 3.5. All right, so that only gives me 2 points. I need one more point. So now I'm going to have to, unfortunately, just plug and chug into the original equation, or the simplified equation, and find me another point. So I get to pick my x. Let's pick an easy x. Let's pick 2, because it splits that distance between there. Let's pick x equals 2. Let's find my corresponding y. All right, so 2 times 2 plus 3 over 2 minus 4. All right, so 5 times 2 is 10 over negative 2, so negative 5. That's another point. So 2, negative 5 is going to be another point on my graph. So 2, negative 5. 2, 3, 4, 5. Here again, I'm counting from the origin. All right, let's rotate that point. So 2 left, 7 down. So 2 right, 7 up. Also a good drink, right? All right. So there's one piece of my graph, and there's my other piece of the graph. Try to hit that point better than I did, okay? Let's hit that point. Let's make it my graph a little bit wider. Okay, so there's that rational function. All right, domain and range. All right, let's see. We don't have any holes. We don't have to worry about that. So this is all reals. X cannot equal 4. All reals. Y cannot equal 2. All right, you can check your answers on the calculator, graph these and look at the pictures and check your table. So like I said, it's a good way of checking your answers if you're unsure of what your answers are. All right, different cases. Like I said, we got to go through all the different cases. So case 3, how does the degree of each polynomial help? Okay, so let's look at f of x equals x plus 1 over 2x squared plus 5x minus 3. All right, first thing I'm always going to do, first of all, let's look at our degrees. I've got my degree of my numerator is lower than the degree of my denominator. So from our guidelines, we're going to see that this is not going to have a, that the horizontal asymptote is going to be 0. I'll show you how we can use that degree trick that I was using before to find that horizontal asymptote. All right, let's factor first, though. X plus 1. All right, what multiplies to give us negative 6? A times c, and has a difference of 5. So it's going to be 6 and negative 1. All right, so take a moment and factor that. So we should end up with 2x minus 1, x plus 3. Factoring makes it really easy to find those horizontal and vertical asymptotes in your x and y intercepts. All right, whole. There's no common factor, so there's no whole. None. Vertical asymptotes. All right, notice here we have 2 zeros for our denominator. That means we have 2 vertical asymptotes. So set 2x minus 1 equal to 0. So x equals 1/2 is a vertical asymptote. And set x plus 3 equal to 0. X equals negative 3 is a vertical asymptote. We've got 2 vertical asymptotes. So let's graph those. So x equals 1/2. And x equals negative 3. So that means this time, since I've got 2 vertical asymptotes, my graph is going to have 3 pieces. It's going to be something to the left of the asymptote, something in between the asymptotes, and something to the right of the asymptotes. All right, horizontal asymptotes. All right, remember we got to match the degree to the numerator and the denominator. Well, these degrees don't match. The degree of the denominator is x squared, so 2x squared. There's no degree to match it on the top, so that means we're going to put in a 0 placeholder to match that. Simplify that, and you get 0. So that's why when it's bottom heavy, the horizontal asymptote is always 0. All right, so that's our axis. Horizontal asymptote. So if you want, like I said, you can still dot it in on top of the axis if it helps you when you graph it. All right, x-intercept, the 0 of the numerator. So what makes x plus 1 equal 0? X plus 1 equals 0, x equals -1. So this is a point. So we got -1, 0. Always write x-intercepts as points. All right, y-intercept, we're going to plug 0 in for all my x's. 0, 0, 0. So that leaves me with 1 over -3, which is -1/3. All right, this one, unfortunately, we're going to have a lot more plugging and chugging to do. So let's get some points in here. Let's graph what we got and try to get the points off of that. And it's all recognized, like doing enough of these that you kind of look at these and kind of get an idea of what the picture looks like in your head before you even get started. Okay, so let's graph -1, 0. Here again, we're counting from the origin. So -1, 0. There's a point. Notice it's touching that horizontal asymptote. All right, because it's in between the two vertical asymptotes, sometimes your graph will cross a horizontal asymptote. You're never going to cross a vertical asymptote, but sometimes between your graph will cross a horizontal asymptote. Horizontal asymptotes are respected by end behavior. So the middles can sometimes cross a horizontal asymptote. I know it's a lot of stuff to remember. That's why I like to say big kid math. All right, that's not going to help us. That's not going to get us any more points. So let's see. We got 0, -1/3. That's my y-intercept. So we here. All right. Well, that one we can rotate. Okay, so that's going to go, so this is kind of like we can get another point over here. So we're going to go, this is going to be 1/3 up instead of 1/3 down. So, all right, so we're still respect to horizontal. So we got the middle piece. We still got to do 2 more pieces. There's my middle piece. If you're not sure about where that second point goes, you have to plug in values. Plug in values and find it, okay? All right, let's go. We got to get some end pieces here. So something to the left and something to the right. So now, unfortunately, like I said, we're just going to have to pick points and plug them in. Okay, let's see what we got here. Let's plug in 1, 2, 3. Let's go plug in -4. Let's let x equal -4, and let's find our corresponding y. So -4 plus 1 over 2 times -4, which is -8 minus 1. And -4 plus 3 is -1. All right, what do I got? -3 over -9 times -1, which is -3 over +9, which is -1/3. All right, so -4. Here again, I'm counting from the origin. 1, 2, 3, 4, -1/3. All right, so now I can get another point off of that one first. So now I know my graph's going to be in this piece and over here because it has rotational symmetry. These have rotational symmetry. So I can get, so counting from where they intersect, okay, that's going to be my counting. So I went left 1 down a 1/3. So I'm going to go right 1 up a 1/3. Like I said, this is a much harder graph, harder concept to do. All right, let's plug in. Let's at least get one more point on that side over there. So let's pick in another value. All right, I'm going to put in +2 because, like I said, my numbers are going to get so big. I'm trying to keep my math as easy as possible. I could use it on that left side or I can do it on the right side. All right, I'm going to go x is equal to 2. All right, let's find the corresponding y. So 2 plus 1 over 2 times 2 is 4 minus 1. 2 plus 3 is 5. All right, what do I got? 3 over 3 times 5, well, that's going to be 1/5. So 2 1/5. All right, so here again, counting from the origin. So I could go 2 up just a tiny bit. All right, now I can get, it's like counting from my red dot now. So I went over 1 2/3 up a 1/5. So on here, I'm going to go over 1 2/3 down a 1/5. All right, so it's respecting those asymptotes. Kind of if you get that curve, that's pretty much what you're looking for. Then you can respect your asymptotes for the rest of it. So here is my graph. That's would be a better curve. It's not a corner. It's actually a curve there. And we'll practice these in class too. So like I said, you can please ask if you don't ask questions. Write down questions as you go through this. That way you can remember what you need to ask in class. Things you didn't understand. All right, domain. It's all reals, but x cannot equal 1/2 and -3. And my range is all reals. It's all reals, right? All right, we typically, it's our horizontal asymptote, but because of the nature of this particular graph, it does cross. Y can be 0 there, because that middle, so it's just the all reals. There's no restrictions on our range here. So like I said, they're all in this, you got to think about the different situations. Unfortunately, it's not one size fits all kind of math. All right. All right, two more. Let's do two more of these. Let's look at this one. Will the asymptotes always be horizontal or vertical? Vertical or horizontal? All right, let's look at this type of question. Okay, so first of all, what do we do first? We always factor. So let's factor out the x. I've got x plus 2. All right, is there a whole? The answer should be no, because there's no common factor, so we don't have a whole. All right, vertical asymptote. It's the 0 of the denominator. So that gives me x equals -2. So let's graph that. X equals -2. All right, horizontal asymptote. Okay, let's match up those degrees again. So the degree of the highest degree of my numerator is x squared. So that means that I've got to match it with the same degree in the bottom, which I don't have. So I put in my 0 placeholder. Well, that's undefined, right? 1 over 0 is undefined. So that means there's no horizontal asymptote in this. If it's top heavy, going back to our guidelines again, if it's top heavy, then you're not going to have a horizontal asymptote. Now, if a horizontal asymptote doesn't exist, you need to look for a slant asymptote. Slant asymptote. So in a slant asymptote, all right, occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. So the degree of the numerator is 1 higher than the degree of the denominator. So in a way to find this, I'm looking here, we're going to use long division. This is the one reason why we learned how to do long division, so we can use it here. So we use long division to find the equation of the slant asymptote. It's always going to be a line. It's always going to be linear. So let's go back and look at that. Okay, so let's see. So we have, so notice here that the degree of my numerator is x squared, and the degree of my denominator, the degree of my numerator is 2 for the x squared, and the degree of my denominator for the x to the first is 1. So we're going to do long division to find my slant asymptote. So we're going to have x plus 2 divided into x squared minus x. All right, divide. X times x gives me x squared. Distribute. Change the signs. So this gives me -3x. All right, I need to bring down my 0. All right, x into -3x goes -3. Now here, once I get this up here, I don't care about the remainder. All right, that's going to give me my slant asymptote. I don't care about the remainder. So y equals x minus 3 is my slant asymptote. So let's graph that. So that's a line with the equation x minus 3. All right, so it has a y-intercept of -3 and a slope of 1. And you want to take this thing, I know my graph is big because we've got to pull out these, it goes all the way out this graph. Slant asymptote, let's go down the other direction. Okay, there's my slant asymptote. So when I do my counting now, I'm going to be counting from where these two graphs intersect, here. All right, so okay, let's go back to the math that we know. Okay, x-intercept, the 0 of the numerators. So that means, all right, so that means we have 2 x's up there, so that means I have 2 x-intercepts. So x equals 0, so 0, 0 is an x-intercept, and 1, 0 is an x-intercept. What makes my numerator 0? All right, y-intercept, well, since you've got x-intercept 0, 0, you know your y-intercept 0, 0. Or plug zeros in for all of your x's, and you're going to see you're going to have 0 over 2, which is 0. So let's graph those points. Here again, we still have that rotational symmetry. So this graph is going to, because it has one vertical asymptote, it's going to have two pieces to the graph. All right, let's graph what we've got. So I've got 0, 0. So that'll give us a point. Or here again, I can count from where my two asymptotes intersect. So this could right 1 up 5. I'm sorry, right 2 up 5. So I'm going to go left 2 down 5. All right, that gives me a point. All right, let's graph 1, 0. All right, and that's going to give me a point. So that's what? Right 3 up 5. So let's go left 3 down 5. All right, so here we got 2 points. They don't really tell us much. They're not side by side. Our graph's going to dip down in here. Since they're so close together, it's going to dip down just a bit, and it's going to dip up just a bit. All right, but we've got to respect those asymptotes. All right, let's see. Let's put in -1. Let's plug in at least one more point to get us. Let's plug in x equals -1. So that's going to give me what? Y is equal to -1. -1 minus 1 is -2. And -1 plus 2 is +1. So that's going to give me 2. So that means -1, 2 is another point. -1, 2. All right, so let's rotate that. So it goes right 1 up 7. So left 1 down 7. All right, okay, so let's draw my graph. So I'm going to respect my asymptote, turn around a little bit, and then respect my vertical asymptote. Here again, vertical asymptote, turn around, and then follow along my slant asymptote. All right, let's see. Let's do one more type here. Are there any surprises? So it's case E. I know these loads are longer than before. Just like I said, it's a more complicated lesson. All right, are there any surprises? All right, first of all, let's factor that numerator. So let's factor that numerator. We're going to pull out a GCF of 3 and then factor this. All right, so take a moment, factor that numerator. You should get 3 times x minus 2, x plus 1. Let's factor the denominator. You should get x plus 4, x plus 4. All right, we don't have a common factor, so that means we don't have a whole. So no whole. All right, the 0 is the denominator. We still just have one vertical asymptote. So that's going to be x equals -4 because it's the same factor twice. All right, horizontal asymptote. The degree of the numerator matches the degree of the denominator. I'm looking at this. So the coefficients, 3 over 1 gives me 3. So I have a horizontal asymptote at y equals 3. All right, so x equals -4. And y equals +3. If you have a horizontal asymptote, you're not going to have a slant asymptote. You can't have a slant asymptote and a horizontal asymptote in the same graph. You can vertical asymptotes go with either one, but slant and horizontal are never together. Okay, things you got to learn about these things. Okay, x-intercept, zeros in the numerator. So we got 2 factors, so we're going to have 2 zeros. So 2, 0, and -1, 0. All right, y-intercept. Let's plug zeros in for all my x's. So that leaves me with -6/16 divide by 2, so -3/8.
Good afternoon.
Let's start to graph this now. All right, let's graph what we have. All right, let's put our points in. So we have 2, 0, 2, 0, and we have -1, 0. All right, now this one, like I said, this is a special case. Because the fact that we have a common factor in the bottom, this is not going to be rotationally symmetric anymore. So that means we can't rotate those points. We're going to have to plug and chug to get the rest of those values. All right, so we got 0, -3/8. All right, so we're going to have to plug several values in here to figure out where this graph is going to go. And the way I recognize that is the fact, like I said, that it has a common factor in the bottom. It's a perfect square trinomial. That's when we're going to have this situation. It's all about kind of recognizing the patterns in these things. We're not always going to have the exact same pattern. So let's plug in some values. Let's plug in, let's say x is equal to -3. Let's find out that one first. So x is equal to -3. Let's find my y value. All right, so let's see. Let's plug in y is equal to 3, -5, -3 plus 1 is -2, over -3 times, or plus -3 plus 4 is 1, and -3 plus 4 is 1 again. So what is that going to give me? That's going to give me 10 times 3, which is 30. So hence you see why my graph is so big. All right, so -330, which is going to be way up here somewhere. All right, so that means we're going to respect that asymptote. All right, and then remember, end behaviors, you can cross, but the end behavior is going to respect the horizontal asymptote. So that thing is going to come down here respecting that asymptote, turn around, and then it's going to come back up and respect that horizontal asymptote. So let's figure out what the rest of my graph is going to do. And like I said, I know this one is, like I said, that's why we said, are there any surprises on this one? All right, so I need to work on that left side of that graph. So it's still, because it has one vertical asymptote, it's going to have two pieces to my graph. And unfortunately, I'm not going to be able to count and cheat and find my other points. So let's plug in, what is that, 1, 2, 3, 4, 5. Let's plug in -5. So y is equal to -5. I got 3, -5 minus 2 is -7. -5 plus 1 is -6. All right, over what? -1 times -1. So that's going to be 42 times 3. So that's going to be 126. Whoa. So -5, 126. So that's way up on my graph. That really didn't help me any. All right, let's pick a point further down here. Let's go, what we got? That's 4, 5, 6, 7. Let's do -8 and see what we get. I'm just, like I said, you got to just pick points until you get a good idea of how that picture is going to go. Sometimes some things require more work. All right, -8. Let's go. All right, let's see. 3, -8 minus 2 is -10. -8 plus 1 is 7. I'm sorry, -7. Over -4 times -4. All right, what is that? 70 times 3 is 210 over 16. All right, so 210 divided by 16. So that is 13 and 2/16, which is 1/8. Okay, let's see if we can get that on our graph. I'm doing this after school, and so I keep pauses in the videos because they keep coming on with announcements, so I keep stopping the video. So hopefully, yes, like I said, it's not going to be too bad. All right, let's graph this. So I got -8, 2, 3, 4, 5, 6, 7, 8, and 13 and 1/8. All right, so up here. All right, let's pick another point. Let's pick something way down on our graph. How about if we do, I need at least one more point. So I know this thing is going to come up here. All right, it's all about where it's kind of turning around kind of thing. So let's see. Let's put in 10. X equals -10. X equals -10. X equals -10. All right, y is equal to, let's go. Let's hope this does it. -12, -11 over -10. That's -6, -6. What do we get here? All right, what's that going to give me? Well, actually, that doesn't work out so bad because I get, this is 36 over 36. When you simplify this, you're going to get positive 11. So 10, so negative 10, positive 11. Alright, so it's kind of turning around there, and it's going to get to that asymptote. It's not going to very quickly get to that asymptote. Plug in more points to get a better graph. It's over like get a sketch of this picture. Alright, let's do domain and range real quick. Domain and range. And we'll be done with these notes. I know you're going to be glad. So this all reals. We got x cannot equal negative 4. Alright, careful here again. It's crossing that horizontal asymptote. So that means our range is just all reals, because it crossed that horizontal asymptote. If it didn't cross the horizontal asymptote, then it would be y cannot equal 0, not equal 3. Alright, so kind of recap on this difficult question. And like I said, I know this one was harder. You can cross, in behaviors will never cross horizontal asymptotes. Sometimes within the middle of your graph, it will cross a horizontal asymptote, but in behavior is always going to respect the asymptotes. And your graph will never cross a vertical asymptote. All right, there we go. Write down questions as you got them. We'll talk about them in class. Thanks.